So what is the geometric ingredient that is created by this inner product equipment is norm. All right? And next one is called the metric. And more specifically, angles. These three things are created by this inner product. Abstract vector space, such as a vector space of a polynomial. Now there's a norm and metric and angles are created. So here's what we mean by norm and all those things. This is R3. This is familiar. And there is this position vector v in there, right? And we use this absolute value notation for the length of the vector. In Calc 3, I think we use term length. But this length in abstract vector space is called a norm, right? Norm of a vector. So what is a normal vector? It is denoted like this. Anybody know the definition of this one? It's a square root of VV, but not dot product, right? But the inner product. So it's always a positive at 0. It makes perfect sense. So that's the norm. It's the length of a vector. So for example, it creates a silly thing. There's an example in here. All right, we're in space. A function sine pi x. Do you see this as a vector? You're seeing the abstract linear algebra. You should be able to see this as a vector, right? Sine pi x is a vector in the space of functions, right? So what is the length of this vector? That's what we're talking about. But the correct term is what is the norm of this vector, right? It is depend on what kind of inner product we're putting in there. So let's say inner product, we define it here. So here's f and g, right? These are vectors. So let me use 0 and 1 here. I'll use a 0 and f times g dx. That was the vector, right? So what is this norm in here? It's the square root of 0 to 1 of a sine squared pi x, right? dx. That is the length of this vector. That's the norm of this vector. Right? There's a double angle formula, remember? Those things, 0, 1. I think that's 1/2 minus 1/2 sine 2 pi x, I think dx, 0 to 1, under square root. Okay? Sine 2 pi x from 0 to 1 covers 0 to 2 pi, right? Remember sine going up and down, they cancel exactly. So that's going to be 0. So that's 1/2. So square root of 1/2. That's the length of sine pi x, according to this inner product. They gave you the inner product, you just mechanically calculated the length of the function sine pi x is 1/√2. If you understand a little bit more about what this inner product is about, and then you will believe that this is a meaningful quantity. Here is a meaningful quantity because you see it as a picture, right? The norm here is just mechanical calculation. I don't know what that means, but that's the length, and hope that makes sense later. But that's the machinery is created. So another thing is as vector v, what is the length of the vector v if this matrix is given by 2, 1, 1, 1 like this, right? What is the length of this vector? In R2, it will be √5, right? But it's not R2. It's R2 equipped with this new length formula, new inner product, right? So what is the this thing is a square root of VV, right? That's what it is. So that's what 2, 1 here. Do you see what that is? A 2, 1 is that 5? 2, 1 is that 3? You agree? That's a 2, 1, 5 and 2, 1, 3. So what is it? Is that 10 plus 3? √13, right? That is the value of this thing. So now we're looking at, so you think there is R2, the familiar space, there is this 2, 1. That position, that length is now reassigned according to this metric 2, 1, 1, 1, right? What is the length of this one? The new length assigned is a √13. That is a new space created. That's the norm, first ingredient right out of this inner product space. And second one is called distance. If you're in R3, we have no problem looking at, here is a position vector v1, here's a position vector v2, and there's the origin 0, 0, 0 here, right? What is the distance between that? That's the perfect term for that distance, right? Now this can be thought of it if you have an inner product, this notion of distance kicks in too, and that is called metric, induced by this inner product. It is defined like this. Metric between the two abstract vector is the norm of the difference of the two vector. This fits perfectly into that. If this is an R column vectors, and if you're in abstract inner product space, the metric is the idea of a distance. They use the word term metric because you can't see these things, not something you can see. We only create like this. This is how you create abstract geometry. All right, here is idea, another example of a metric. For example, this notation is introduced in the book. Do you know what that is? Instead of all continuous function, only considered over the interval 0 to 1. All continuous function. Do you see that as a vector space? You thought about it, it is a vector space. If you can add two functions and scale a multiple over the real coefficients, so if you assume these are real coefficients. How about inner product? What is inner product of two functions there? Since we're looking at 0 to 1, why don't we take that again, right? That's inner product. Good. Now we're talking about the metric between two functions, sine pi x, and if you look at sine 2 pi x, I think 2 pi x is what I probably wanted to, sine pi x, and x minus x squared. Sine pi x is one function in abstract vector space. X minus x squared is another function, right? We're talking about what is the distance between these two functions, which is actually the correct term is metric. So how do you calculate that? It's a sine pi x minus x minus x squared. Distance between these two vectors, right? So how do you calculate that? Square root of 0, 1 of this vector inner product itself, right? So here is a sine pi x minus x plus x squared, and to itself that is going to be squared, right? And here's a dx. Like that. Whatever this number is, that number is a distance between these two vectors. Okay? All right. So I think I better explain a little bit here. Whatever you define, that's in the geometry, but why is this meaningful for computing anything about this function, which is one of the goals of this whole thing, is the following. This metric supposed to measure, so sometimes it's called a metric space. Inner product space is a lot richer structure. It comes with a norm, it comes with a metric, and it comes with the angle notion as well. A lot richer. But metric space is only focusing about metric, distance between these two things. Which one is closer to which? Okay? So all you have to believe is that if I'm looking at v1 minus v2 like this, if it is a metric, if it is really measured metric, if this metric is almost close to 0, what does that mean? And they're almost likely same to each other, right? So we have to understand this inner product definition and induced metric really measures two functions being almost equal to each other. If this value is very, very small, for example, if this value is very small, we should believe that these two functions are really almost the same. If numbers are same is easy. How are you going to measure the two functions as the same, almost the same? That's what we're trying to do, right? Their idea is like this. If two functions are very, very close to 0, the metric we just defined is a 0, 0, then somewhat we have to believe that these two functions f and g are almost the same function. So if you sketch it, so what is the metric here? Let me just use squared version. If it is close to 0, square is close to 0 as well, right? So just to ease that part, so that's a 0 to f minus g squared dx. That was the definition I introduced, right? If it is very, very close to 0, why should I believe this two function is very almost the same function? That's what I have to explain. But that explanation doesn't have to be part of the definition. So here is the thing. Here is a function, and between 0 and 1. Let's say f looks like this. And I sketched the other g that we discovered, a different function. Maybe this is a polynomial and g is a trigonometric. And I calculated that. Sketch the function, it looks like something like this. I sketched these two functions, it turns out like this, and then you believe, and that function is almost like same to each other, right? You will believe that, right? And this mechanism actually guarantees that if you actually sketch g and f like that, their pictures are almost like this. Not much of a difference. Let's see why this is so. What is f minus g measures? Difference between these two functions, right? That is really this thing right here, right? N squared. So if this is a very, very tiny thing, if it's squared, it's still negligible. The reason they're using the square version is algebraically easier to handle. No, it's just an arbitrary polynomial, but it is kind of compared to the Taylor polynomial, but it is not the Taylor polynomial. There's a significant difference between these two things. This is called global approximation. Taylor polynomial is local approximation. It's about one point. How well can we do around that one point, right? This one is that I have an entire interval 0 to 1. What is the best way to approximate that value? So that's the difference. Here, if you measure the other one, there's a tiny thing, but although it's, so f is bigger than the other, it's a squared, it's all the same. So what does that measure? It kind of difference between that gap, right? If this is very, very close to 0, would you believe that if you sketch it, always it's just right around that corner? So you will believe that. That must be pretty the same. You can think about a pathological example that here's an example, but my example is actually like this. So still, it is very small, but somewhat in differential derivative-wise is very different, right? So if you remain in this inner product, you may happen to allow this kind of very, very fractal kind of example happen to be your approximation as well. But if you stay away from the fractal kind of example, just typical elementary functions, sine and cosine and polynomial, these things usually don't happen. So this really captures nicely about polynomial don't have this crazy behavior usually. So if you have one transcendental function, if you wanted to use polynomial, then it is really a very nice approximation. So I hope that convinced you that this inner product they define and induced metric, really the picture is approximately the same if the metric is this distance metric is almost 0. All right, that's the idea behind it. So that's metric is another one. And yeah, another crazy example in here is really the crux of the modern geometry. Here is xy plane, and this is the unit. I don't know. Unicircle is no longer a good word. It's just a locus of this equation x squared plus y squared equals 1. Now it has a new metric given by this inner product which is defined by this 2, 1, 1, 2. That's the metric, right? If you have a metric, then we have distance between the two functions and 2 points in here given by this new metric, not usual distance, right? So here you see this distance between these 2 points in here is 1 because of this, right? But according to new metric, is not 1. According to that new metric, is not 1. You have to go by this new metric system, whatever that is. So entirely different metric is proposed in here. This arises in a modern physics setting like this. Suppose you are in inertial frame. I hope you know what that means. You are here, and you happen to be the inertial frame. The physical phenomena that's happening around you, it is not weird. It is just, it's very, very normal. There's a way to detect that. And this one is something you're observing. The other guy is out there, and guys are there. What is happening around him is what we're observing in here. But this guy is moving. As soon as they're moving in different directions, the special relativity says that what you're observing is not the same as, for example, if you distance from here to there, to him, it is 1. But when you're looking at it here, it turns out it's not 1. For example, the light travels from here to there, and the time it took is different from the other one. although you look at it just like this. So special relativity suggests that if the other guy is moving and the metric you observe from the other person is not the usual metric, a different metric arises. So how long is he going to travel from here to going from here to there is not like, okay, that's 1, therefore is that. You have to go by different metric to interpret correctly from observation. Right? That is a beginning of a special relativity. The metric system in here is defined all across, and then you have to go by that to calculate that. So what is the distance all around the circumference? And here you have to use this metric to calculate that. That's a special relativity analog. If this guy is not moving at a constant speed, but it's accelerating, then this one is really getting complicated. Right? So that's the general relativity. Right. Here is the interesting part of a new geometry that is what you're entering. I'm going to show you how to actually calculate the circumference of the circle according to that new metric. That means if this guy, if certain particles travel around the other guy, how long will it take if it is constant speed? And then it depends on how long the distance is in that metric over there. All right? So here it is. You can still parameterize this one like x equals cosine t, y equals sine t. All the positions is the same, right? Is the distance is interpreted differently. Okay? So here the idea is that you divide t between 0 and 2 pi into various different values tk. t0, t1, that is uniformly doesn't matter. And then you have this point in here, xk, which is cosine of tk. Is that right? And yk is a sine of tk. Somewhere here, t is some, partition. And the next one, it's so usually this delta tk that you learn in time segment that it's divided, whatever. It's not really time; it's just a parameter. Then here's xk plus 1, and you can imagine this is very, very close to each other. And this is going to be cosine of tk plus 1. Yes?
Is there the metric you chose, does it have to be diagonal?
It has to be it doesn't have to be diagonal, but it has to be symmetric for the real. So you can change that to 1, right? It has to be symmetric. So the inner product, v inner product w must be same as the w inner product v, right? Because of that, it has to be symmetric. All right. So you have that. You want to measure the distance between these two, right? Correct? So, so we have this vector, and here, well, distance between this is a vk, and this is vk plus 1. Correct? That's the position vector. What is the distance between vk plus 1 minus vk? Is this vector you calculated. And you can see that this delta difference between these two. So what is the vector? Think about it. So you see that? That is the delta xk. That's the difference between these two quantities, and delta yk. That's the column vector. If you subtract this x and x, the arithmetic has nothing to do with the inner product. Addition and subtraction is still the same. But for that, we have to use the square root of this delta xk, delta yk, new metric kicks in here, 2, 1, 1, 2, and delta xk, delta yk, square root. That's the distance between these two things. All right? So I'm going to skip that calculation, multiplying it out. I remember how it looks like. So it looks like this, 2 times delta kx squared plus 2 times delta xk, delta yk, and 2 times delta yk squared. This measures distance between these two things. If it is a normal metric, right, usual space, that will be just delta xk squared plus delta yk squared, and that's it. That's just the usual Pythagorean theorem to measure this one. Now we have a new metric to compute this distance between these two things. So this is it. All right. So if you sum this all up, and that will be the approximation. But usual calculus technique is that there's a parameter behind this one. So they stick in this parameter like this, delta xk squared, divided by delta tk. That's the parameter behind it. You stick it in there like a square. And here 2 times delta xk, delta tk, you stick it in there. Delta yk, delta tk, you stick it in there. 2 times delta yk squared, delta tk squared. Stick it in there. So you put it in the denominator. So what should we do? You have to cancel it outside with the tk there, right? So they cancel out and remain the same quantity. Now this delta xk divided by delta yk, do you know what they do in calculus about this one? Derivative. Excellent. It is not equal to derivative. And that's the part that, because you're entering the weird geometry, what is happening to the error has to be carefully thought out. Is that reasonable? Because you can't see this anymore. You can only rely on this mathematics. So when you approximate this one with x prime and tk, right? X is given by cosine t. Therefore, this one is approximately negative sine tk, correct? So this value is very, very close to negative sine tk, but it's not the same. There is error term. How is this error term behaving and understanding very clearly when you sum up infinitely many, and you have to argue that they're actually negligible. Therefore, just replacing this one with this approximation for the integral purposes is okay. That is absolutely not clear here. So you have to kind of argue that nicely, but assuming that the sum of all this thing, k going from 1 through n, right? If n is like a million and all that, I just try to explain that this is actually approaching to this one going from 0 to 2 pi. This one is replaced by now 2 times, if I call that one x is given by f of t in general, g is given by y is given by g of t, which is cosine and sine I already mentioned. Then here's a 2 times f prime of t squared, and 2 times f prime of t g prime of t plus 2 times g prime of t squared. And there is this delta tk becomes dt outside. All right? This measures the length of this whole circumference around this path that looks like a circular to us. But this is the metric they're experiencing, right, in the relative situation. All right. So, kind of each of this spot, and here, if you look at it here, this length maybe it's, if you actually sketch it, you can get that usual metric. But if you according to the formula, there's a little stretch factor. If you look at over here, that length exactly the same length and in here usual metric. But if you use this one, it's a stretch in it by different factors. So that factor is called a Jacobian. Do you remember Jacobian from Calc 3? Yeah, when you do the double integral or a different integral, the idea of integral factor, there is this multiplicative factor coming in and kind of changes the integral formulation. And the key thing is that here that factor, stretch factor, there the stretch factor is all different. So integral gets more complicated. Right. So anyway, that's new metric is generated by that inner product, and new geometry was defined. Okay. So here is the usual metric space. New metric is defined. This space is called a Riemannian metric space. That Riemannian metric space inspired Einstein, and Einstein developed something called semi-Riemannian geometry. Right? That using the way the light travels and stuff. All right, so next. And another metric, important part of the metric is that metric happened to be the important part of abstract mathematics, and later on you might experience. So here's a more metric formula for the metric space. How about this one? If I have one vector, another vector that's less than or equal to this vector, another vector. This is called triangle inequality, and this is coming from it only using the metric idea. And how about this one? What's a strange formula? Anybody remember this formula? 2 times p1 squared was a parallelogram equality or something like that. It's 2 times w squared. No, it's a plus, and here's a v minus in there. Yeah. And then there's a Pythagorean theorem that, like that, is v squared w squared, right? Whenever there's orthogonal. So this is not really metric space. Metric space does not have an angle, right? So this statement is actually not in the realm of a metric world. But metrics as a metric space, and this is triangle inequality. And it's semi-Riemannian that Einstein's space-time breaks this triangle inequality. That one is named space-time twin paradox. The space-time twin paradox is simply if you go around here like this in a space-time, and if you go like this, if it is a usual metric system, doesn't matter what the metric says, this takes longer, right, than going like this. No matter what the metric is, that's what it says. But space-time breaks this one. So if you go around like this, it is actually shorter than going straight like that. So that is a different space, the different metric is. But the mathematics, the flavors of mathematics going in there is all the same than what we do it in here. Back then, mathematicians didn't care about inner product to itself being negative number. Why is that meaningful? Had no idea why would that be application. But space-time was the first application considered. That all right, we have to allow this thing being 0, and then let's rewrite this entire inner product business again, allowing this thing to happen. But usually it's the positivity we wanted, right? Yeah. All right, so that's the metric space. It's gigantic entrance. Gauss and Riemann and Ricci and Einstein, all these people enjoyed 200 years developing this one to rewrite entire science, again, using this gadget. All right, to the angle now. Third ingredient is angle. Not only we have a metric and a norm, we also have this wonderful angle system. In this modern physics, and an angle is in full force is important, but often what is really used about this angle is orthogonality. Is what is used. Okay. So in physics also this orthogonality is used a lot. So let me use this formula. It's a volume calculation. In physics it happens a lot. Calculation. All right. If you have little plate hovering inside three-dimensional space, and suppose that lots of particles going through that plate, and there is a flux calculation. Remember that from Calc 3 or in physics? Flux, things are going through, electric field, particle, the wind, whatever, we calculate this flux. In that flux calculation, and computing the area of this one is the important part. Or if it's like a parallelogram, then volume of this thing is important. Again, like the special relativity, if you're observing this phenomenon from a distance, and this is traveling a certain distance, that what you see is not really the area. So here's again, if you're looking at xy plane like this, and with a metric given 2, 2, 2, 1, 1, 2 like this, and if you're looking at, I chose this special one, hope you understand later, 1, 0, and the other one was 1, negative 2, so it's down here. It's 1, negative 2. And you can see the parallelogram Parallelogram creates it. And you can calculate the area of this one, right? Area of that one. What is the area? Bottom is 1. Height of this one is what matters in parallelogram. Height is 2, right? So the area is a 2. But think about it, it's actually happening, some physical phenomena is happening to the other guy. That's the inertial frame for the other guy, and we're just observing it. And what is the flux and what is the area he's measuring there is not this one. It is actually through this metric. All right, so let's look at it here. 1, 0. The relationship between these two things, 1, 2, and 1, negative 2, you see that what that is 1, 0. If you multiply 1, 0, that's a 0 here, right? And that's negative 3, is that right? 1, negative 4. So if you dotted these two things are 0, correct? Yeah. So that means this vector and this vector v1 and that vector v2 to the other guy, they think v1 and v2 are perpendicular to each other. It doesn't look like a perpendicular to each other, but that guy, when this guy is looking at these two vectors, they're actually perpendicular to each other. Right? So in this guy, we'll measure that, all right, here's my v1 to him, and here's a v2. I see these things perfectly perpendicular to each other like this. What is the area? Is the length of this v1 times the length of this v2. That's how this guy measures the area of this one. So relativity is different through this machinery. So what is a v1? It is this 1, 0 and 1, 0 to that, I think, is root 2. And v2, it turns out, is root 6. I did that in here. You v2 itself, and put a square root. So it turns out it's a 2 times square root of 3. We think to us it looks like a 2, but what this guy measures is that this area is a 2 times root 3. Right? So Einstein figured out, using the principle, that how we're going to correctly observe the physical phenomenon is happening over there by observing it, then you have to go through this type of a process. So look at that x, y, so what you see, and metric is completely different. Metric is going through this abstract system. All right? So that's actually serious angle business, orthogonality business that is kicking in the modern physics. How about 3 vectors in 3-dimensional space, and they make this parallel, pipette. That's what they said, right? What is the volume of this one? Then you have to go by actually the orthogonal one each other, not because they look orthogonal, using whatever the metric they have. All right? That's the volume calculation and it is the very important piece of integral calculation, because integral calculation, if you think about double integral and triple integral, it is about how you dissect the volume and multiply the weight and things like that. So this idea goes deeply into we call it geometry of physics in relativity. All right? I'll stop here.